Okay, perfect. Recording has started. I can vent this. Okay. I hope that this is visible to you guys, right? Oh wait, let me actually, like, before I carry on, I'll just look at my other PC and just simply logging in there and actually keep the chat on the other PC on so I can see. Let's hope that I will not have to log out. Okay, it doesn't connect me in. But anyway, like, please send me directly on my chat, like PM, like direct message, not in the meeting, because apparently I cannot join from the other PC the meeting. It's just add this device. There we go. Actually, I could now. All right. So feel free, if you have any questions, I'll keep an eye on the chat window. Like, I'm gonna look at it on the other screen. In the meanwhile, you can carry on. So I hope that this is actually, like, looking at my recording from the other side, it should be readable, right? This is readable, right? Yeah, actually, at least I see it in my screen. I don't know about yours. Is it, people?
It is readable.
Okay,
Yeah,
good.
it is fine.
It is.
Perfect. All right, so let's actually talk about data structures for a minute. Now, if you would like to, why would you like to study data structures in general? Let's actually talk about the motivation here. So let me minimize this. The motivation behind this is we need to know how to organize. We need to organize data in memory. Okay, in order to make it easier, I forgot any. To filter and search through. Okay, so this is one of the reasons why you, for example, need to actually use data structure. So therefore, organizing an actual organizing a phone book. My pose is actually like how I'm holding the laptop is killing my hands, so that's why my handwriting is amazing. So hang on. Organizing a dictionary or a phone book. So if you would like to organize a dictionary of words or a phone book, is definitely or is surely different from how you organize, how we organize a map, right? How you actually hold, or how we actually store, let's say like so, how we store map data. So if you actually look at Google Maps, in Google Maps, you actually you have a graph rather than like it's actually a bunch of graphs layered and layers of graphs and geodetic data rather than a simple dictionary or a hash table or something like that, as we're going to study further. So you need to know, like, for every problem you have or for every problem you face, you need to know which data structure, what is the proper data structure to use. Now, again, there's I would like to mention here that there is no silver bullet for any problem, like for any, there's no silver bullet for everything. So you cannot say, for example, okay, the best data structure of all time is going to be hash tables because I can solve all my problems with it. You don't, because it is efficient in solving certain problems and inefficient to solve other problems. So you need to pick the right tool for the job. And this is the purpose of this class, is to teach you, like, okay, the good thing about this data structure, if you would like to use it, you will use it so you can get X, Y, and Z, but you will miss out on A, B, C. And if you miss out on these guys, then it's totally fine, because this is not your concern for the current product or the current problem you are trying to solve. So it is important that you pick the right data structure for for the job you're actually trying to finish or for the problem you're trying to solve. I'm actually not gonna write like on the same screen here because my hand is actually obstructed by the rest of the laptop. So I'm just gonna scroll this thing up a bit like so and keep writing here until I fix that problem. Now, data structures, let me actually like put this here with some different color here. So in this class, data structures are going to be discussed or are going to be discussed in two ways. The first one is the logical model. Or we can also call it the, some people call it also the mathematical model, but you don't see math equations anyway. I mean, we don't show it here in the class. Or we call it actually the abstract data type. Okay, so this is like the first thing. So what does it mean actually? So what does this mean, an abstract data type? So let me help you out in here. So I'm here not concerned about the implementation detail. I'm only concerned about what the thing is and what it does, right? So for example, let's take as I already like gave an example at the class yesterday. I was asking them, if an alien comes to Earth and they look at your phone and they ask you, what is this thing, right? Can you actually describe it in a way that can be understandable? Can you describe, for example, a phone to a 3-year-old? You see, it's actually almost the same thing, right? So the alien is actually like completely unaware of, the alien does not necessarily understand what a phone is, because they might have a completely different notion of what a phone is. Maybe they don't have phones, maybe they don't use ones, or they don't need one. So you need to describe this. So how can you describe that? Actually, feel free to put it on the chat. I'm actually like kind of curious. How would you describe this? Like what is the job of a phone generally?
Maybe we can say it's a device for communication or something else.
Okay, so if I actually take the phone as an ADT or as an abstract data type, so what the first thing is communication. I.e. phone calls or calling, or actually to be precise, voice call. Wow, I'm really like stressing my my wrist here just to get my hands in. Okay, let me just push this up a little bit like so. Okay, 2. Okay, so originally long distance communication. All right, so this is actually the call. So communication, or actually like let me actually put a slash here, long distance, because we are actually quite limited as species. So long distance communication, which is freaking awesome when you think about it. Okay, next. Can anybody give me one more thing that the phone can actually help you out doing things? Media sharing. Twine, media sharing it is. Why not? So this is assumes that you are actually connecting. This is actually the modern phone, by the way. So connecting to global network, which allows for media sharing. Okay, 3. Gaming. Yep, why not? Anyone more?
I'm thinking taking photos and videos.
Photos and videos. So photo, video recording. Okay, learning. Oh, that's a far-stretched one, but okay. I mean, I remember clearly, like long time ago, I used to read books on my own phones, and back then the screens were like, what, 3 inches wide? It was super crazy small, but I finished a lot of books that way. But in any case, since you have actually described the phone, like for reading and stuff, right? We can. I need to push this here. Oh, I don't know how to spell today. Apparently, reading. Okay, so this is the phone as an abstract data type. If you have noticed so far, we actually don't care about the underlying implementation. You didn't talk about what is the CPU in there, what is the operating system. You didn't talk about the software which is needed in order to do all that stuff. You don't even talk about the antenna. You didn't talk about the radio. You didn't talk about what kind of radio frequency you need to use. You didn't talk about any of the implementation stuff. All what you needed to say is a phone as a phone is going to be, by definition, a phone of the current age. I'm not going to talk about like the older ages, but anyway, like the current age phones has to do these 5 functionalities. So if I actually come up with something gigantic, like a table size thing that actually does all of these 5 guys, that means it can be actually qualifying as a phone, right? Now, obviously there are many, I mean, right now, actually looking at this list, a laptop can qualify as a phone right now, isn't it? You can actually do voice calls, you can connect to global network, you can do gaming, you can take photos and recording, you can do learning and reading, right? Now, obviously, a phone is right now it became, yeah, we can, the phone actually started to blur this edge of what a computer is, right? I mean, I could run on my phone and this was on my Note 9, actually, I could run a Linux virtual machine. I booted up a Linux virtual machine, and it's a full Linux desktop. I just connected to my screen, and I got a complete desktop operating system, which is awesome. That our phones right now are capable of doing this. And the Note 9 is like what? It's like, I don't know, 5-6 years old. So yeah, it's right now started to blur this. But for example, if you would like to talk about the implementation, right now you need to talk about the nitty-gritty details. Right now you're going to talk about the power budget, the space budget, because you don't want things to blow up in size. You're going to would like to talk about how optimized the software is going to be, the algorithms which you need to run, frequencies which you need to run, like to make the radio waves working, synchronizing with the radio network of the telecoms. I mean that right now the problems, or not the problems, the stuff which you need to solve in terms of implementation detail are like just a huge list of things to do. So when we're going to discuss algorithms, actually not algorithms, basically, but data structures, we're going to discuss them from these two aspects. We say, okay, you are going to be a stack if you implement these functionalities. You're going to be a queue if you're going to implement these functionalities. You can be a binary tree if you're going to implement these functionalities. And when it comes to implementation detail, it's just we don't care how you implement it, right? So, but the main thing that you satisfy these stuff. The implementation detail right now will come next when we say, okay, I would like to use this kind of implementation, not the other implementation, because I would like things to run faster, or I don't care about the speed. I care about, like, I can have a bigger memory or a bigger size. I can manage larger stuff. So we're going to see both. So logical, mathematical, or abstract data type, this is the first aspect. The second aspect is going to be, whoa, that's small. Was it this one? Yep. Or was it this one? Let it be this one for now. Okay. And the second one is going to be the implementation detail. Now, mostly you're going to talk about the implementation detail with Adil, like you're going to see it more hands-on implementation aspect, right? But however, I can actually touch upon code every now and then on my end, just to touch upon certain things. So we can say this, which discusses how we implement an ADT, or an abstract data type, all right? Because a single ADT can have several implementations for the same reason that your phones have a different manufacturers and implementations, and for the same reason your TVs have a different implementations, right? Like you can have the cinema implementation with projectors and stuff, and then you have your TVs at home, and then you can have your computers using as a TV. Like that's why you have like many implementations. So we define the operations with ADT, not the implementation. So that's just to be clear here. And then finally, let me just here, and like what we're gonna discuss here in, let me see, so study, we shall study the cost of using each type. Whether it's a data structure or an algorithm. HM. Okay. So now that's actually out of the way. Let's talk about, today I would like actually to cover lists, stack, and this is it, because I actually like list, linked lists, and the stack, because I haven't made it to the queue with the class, so I'm gonna, if I finish early, I'm gonna stop there. So actually, let's talk about list as an abstract data type. Just take this out, okay. So let me actually like draw a line. Here's gonna be list as abstract data type. Just better. So a list by definition is a collection. Oh boy. Is the space a little bit, is a collection of objects of the same type. And this is super important. You cannot have a list of objects of different types. You cannot have an object where you can insert an integer and a float at the same time. Even the compiler, I think, will not allow you to do so. I think. Even in C#, in C#, you could actually pull that off, but if you are using, for example, array lists, and if you do so, your object is actually, or your float and integer and double are being converted into an object, or boxed rather into an object and inserted. And the array list is actually a list of objects at the end, not a list of specific number type. So if you actually think that you broke the rule, you didn't. You just simply casted or boxed the actual thing into an object. And please remind me about that I actually need to talk to you about boxing and unboxing and programming 3 later. But sorry. So yeah, a list by definition is a collection of objects of the same type. You cannot have different types in a single list, or you shouldn't rather, because it will be meaningless. So what is a list as an ADT, right? So if we actually talk about the ADT bit, abstract data type, you need to actually store the number of elements somewhere. I mean, not somewhere precisely, but of a given data type. Okay. You need to actually write. So what are the job of a list, right? So what qualifies a list? You need to store the number of elements. You need to be able to write at a given position or at a given index. So write at a given, or actually not write, but rather insert. But okay, let me insert at a given index. Okay. Modify at a given index. Remove at a given index. Okay, so you have that. So you have these operations in order to actually like define what a list is. Like if you have these operations implemented, boom, you got actually a list by definition. Okay. So how it would be, for example, when it comes to like, how can we implement this, right? So you actually say, like, if somebody actually comes to you at a certain point in time, and then he gives you a paper of specifications, and the guy or the girl asks you, okay, I need to fix this problem, and I need these guys to be done, okay? Like these guys to be implemented. And now the implementation detail is falling onto your shoulders, and right now you sit in front of the PC, you open the IDE, and then you start typing some code. But how can you solve this? There are actually, well, there are many ways, but the most popular ways of implementing a list, there are two of them, which is an array implementation and a linked list implementation. Okay, so you can actually pick which one of them you would like to actually use in order for you to solve a certain problem. Now, and each one of them has their pros and cons, which we're going to actually discuss very, very soon. So the array implementation, if I actually pick up, for example, this one, or okay, let it be so. Array implementation. If I know how to spell or how to write today. So in the array implementation, what you need to have is, one, you need to define the array size. Now, obviously, if you run out of memory, or if you run out of the size, so for example, if you define an array of size 10, and you would like to insert the 11th or the 12th object, or yeah, the 11th or 12th object, what you're going to need to do is to define another array of, so you're going to have like array 2 of a double size. At least this is how list of T in .NET Framework is being implemented. Copy the data from here to here, and then remove this from memory. Okay, so this is how automatically expanding arrays work, and I think you already know this from C++ working with vectors, right? So this is how you can actually do that. And you're going to need to implement this by hand, obviously. This copying mechanism, you have to detect, okay, the guy is actually trying to add more than what the array size is. So you can actually do all these operations. Some people actually need to define the end of the array. In some implementation, it's actually required. So you know where is the end. So you can actually know how far you went in terms of the size. But this actually can be calculated, but fine, we can actually leave it there. Now insert at X, right now you need to actually, how you can actually do the insertion. This is actually a good point. Insert at X, or insert at a certain position in order to make it a little bit more acceptable. Here you go, insert at I, right? Now, if you would like to insert at I, for example, imagine this. You have an array, and then you have like 1, 2, 3, 4, 5, 6, 7, for example, and an empty spot, right? So you have one more spot for inserting an element, and I would love to insert an element here at this index, right? If you would like to insert it right here, you don't want to override this, right? So you would like to keep the 4. What you're going to need to do is shift everybody else to the right and insert your stuff in. So you're going to have 1, for example, 2, and I'm trying to insert, let's say I'm inserting at index, I don't know right now, 0, 1, 2, 3. So insert at 3. I would like to have, for example, number 10, right? And you're going to have 1, 2, 3, 10, and then you actually shift all these guys forward. So it's going to be 4, 5, 6, 7. Okay. So this is how you would do insert at X. Now, obviously, this is more or less an expensive operation if you would like to insert at a certain point and shift everybody else. And again, you don't need to worry about performance that much unless it becomes a bottleneck until it becomes a problem in your code. Always profile your code before you do optimization. Early optimization is the root of all evil, and I always tell that to everybody I was working with. So do not early optimize because you are feeling your computer cannot handle it. Your computer can handle crazy stuff, but if you have an execution budget that says this operation needs to execute in 2 milliseconds, then right now you really need to tweak stuff to be within that budget. Otherwise, you really don't care. But this is at least how insertion works. Now, obviously, if you're going to insert at the end, you don't actually care pretty much. You don't need to shift anything. Just insert the thing in there and you're done. So if the list gets larger, as I said, we already just simply allocate this. Now, here's a small trivia which I asked people about. And you're going to see it actually in books, specifically in the books which I've given. You have an array. So you have an indexing, 2 indexing methods. Some people say array of 1, and this is going to be first element of the array. It's a single off. This is actually the first element. Some people, or in some programming languages, they have a 0 base, like the C languages, which is going to be the first element. And this is going to be also the first element. Do you know why 0-based arrays are existing? Do you know why? Do you know what is the difference between this guy and this guy? Both of them are valid. So I think, I don't know if Pascal or Fortran. I know that Fortran probably they had 1-based array. I hope that I'm not mistaken. Pascal was actually 1-based. All the C-style languages, so C, C++, C#, all of them are 0-based arrays. Or at least we call them, in the jargon, we say 0-based array. In the book of Introduction to Algorithms, the green book, which I've already given to you, like with MIT Press, the arrays which they describe there is 1-based array. So they actually write there in the for loop for I equals to 1 till I don't know right now, less than 10, I++. So they are using 1-based array. Do you know the difference? And it's okay to get it wrong, so feel free to write it down or type or say it through the mic.
One more element.
One more element. Can you please elaborate more?
I mean, int has its limits. Integers have its limits, and it's basically when you start from the 0, you have one more element. I don't know.
Actually, okay. This is, by the way, just here's a small. Here's an interesting historical bit. Some algorithms, some people, when they were coding, they didn't like the idea of starting from 0, and they always started from 1. because they just it didn't feel right to them. And they always had this wasted piece of memory, which is at the 0th position, and nobody actually used it. It's kind of funny thing, but it actually exists in some papers and some books. But what you said is like, this is like, it's actually close to the reality for that historical point of view, which I'm mentioning. But what I'm actually asking about, what is the meaning of a zero-based array in general? Like, why it is 0? Okay. Since no one don't want to give it a shot, this one, let me actually like use another color. This guy is the first element. This guy, when it comes to other programming languages like the C and C++ or C style languages and other languages, this is the offset, memory offset. Do you remember in C++ when you're actually having an array and you have a reference to the array, right? You have a pointer to the array. Your pointer is actually pointing to the first element by default, right? If you remember in C++. And if you would like to move one more, you just simply say, okay, so how far, if I have a pointer to the array, a 0 offset means gives me the first element. The 1 offset means please add, if I have a, let's say that this is a list of integers, or let's say this is an array of integers. You're saying that add 4 bytes of an offset to get to the second element, right? And then the third element, please add 1 more byte to get to the third element. If this is the index, and this is 10, 20, 30, 40, and so on and so forth, this is what actually indices are all about, like the zero-based index. So if I'm saying give me 0, that means that please do not offset anywhere. Give me just where you are pointing at, like the first element of the array, practically speaking. And this is the difference between a 0-based array and a 1-based array. 1-based arrays, in all programming languages, they are literally saying, give me the first element. But 0-based arrays, they are talking about the memory offset, how far I would like to go further. So for example, if I will go to here, that means I need to add, I don't know what was, how many of this stuff? 1, 2, 3, 1, 2, 3, 4. So you need to add 4 bytes in order for you to, actually 4 times 4 bytes, 4 multiplied by 4 bytes in order just to get to the 4th element of this array. Okay, so this is the reason behind it. And now that you know that, how to deal with now that you know actually the difference between 1 and 0, we can actually move along with linked list implementation. However, I'm going to actually give you a small break before we actually carry on. Okay. Do you have any questions before we run to the break?
Is the linked list the chapter we did at exercises? Mislim na vježbama.
Yeah.
Yeah. Okay.
Yeah. Actually, I mean, I think you done. Did you do the? I think you did the arrays, haven't you? The array implementation of a list.
I
Or
think
I'll
this
just
is, imamo čvor, we have a not. Mislim, to je to.
yeah. So probably you have actually like probably Adil actually have covered linked list before the array implementation. But it's okay. I mean, probably he reversed it, but it's fine. So yeah, this is actually what you have covered in the classes. And once we finish this one really quick, we move to stack, which you should be covering this week.
Okay.
Okay. Are there any questions regarding what has been covered with the arrays? Okay, if there is none, I will actually give you a break of 10 minutes. So right now it is 1 and 2. I will give you until 1 and 12. So see you by then. In the meanwhile, if you have any questions, feel free to type them in and I will answer them. right. 13 both. Let's actually move on. So linked list implementation. As opposing to arrays, linked list is simply a list of elements where each element points to the next. Okay. Now, if you actually open a book on data structures or generally on linked list, or you actually read an article, there are many flavors of how people are actually showing this thing. So basically speaking, if you have a linked list of integers, let's say, they would actually say like this. So they say, okay, here's your one, and then you have a tiny box pointing to the next element, right? This is how they draw it, at least. And then you have a pointer to the next element, right? So now here's the interesting part. Some people like to represent it that way. Let's say that the 3 is the last element. So if 3 is the last element, they say it's pointing to a null object. Okay, so this is like the same normal element. It's just a null object. Some people like to actually, instead of having this flavor, so you have, everything in before, and then you come to 3, and then they have a null pointer. So there is a difference between pointing to a null object and having a null pointer. Okay, and I think you already have seen this in C++. Like, well, actually, like you have seen in C++ null pointers, but probably you haven't seen null objects. I mean, you can create an object which doesn't hold anything, which is going to be null, I think. But there is actually a pattern, a software pattern called Nullable Objects, and no, sorry, not Nullable Objects, but the Null Object pattern, which and this is happening because, and everybody had it already, the null reference exception. You are referring to something that doesn't exist, right? You are having this invalid memory addressing of object, referring to something that doesn't exist. And the people actually got sick of it. So what they did was they created a specific class, like it's a software engineering pattern where people create a specific class, they call it the null object, right? And whenever you have something that doesn't exist, they don't say, for example, x equals to null. Come on, cooperate. They don't say x equal to null, but they say x equal to new and that class, which is called the null object. Okay, and this is just to avoid the null reference exceptions. So if you have some sort of an object that just doesn't cooperate with you, people don't just have this. I think I've seen this somewhere in production, where people just simply use this pattern so they can actually escape this. This is you're gonna probably study about this more when you get to Eres and Eres Dua. I think maybe it will not be taught, because I mean, I don't know whether it's popular or not. I don't like the idea of it, to be honest. But yeah, it's people just like to protect themselves from having null reference exceptions. So they created this null object, which is something similar to this guy. Okay, so this is a pattern actually existing. So if you actually open a book on software on data structures, you might actually see one of the two representations, and both of them are valid. Okay, both of them are the same. Okay, so one of the interesting stuff about linked list is that you don't need to define in the implementation detail. When you think about it, you don't need to define a size because you literally don't care. All what you care about is having a pointer to the last element. Well, okay, you need to have a pointer at the head, practically speaking. You cannot have a pointer to the last element per se, but you need to have a pointer to the first element. And if you would like to insert something at the end of the linked list, all what you need to do is for loop until you find this guy or this guy, the null pointer. And then you say, okay, they are not going to be null anymore. I'm just going to make you point to 4, for example. Right? Which you already have seen with Adel. And make 4 this actually pointing to a null. Right? So this is going to be the last element of a linked list. Now, the interesting part about this is that if you actually look at this, you have a problem where insertion is actually becoming a little bit expensive because you are hopping in memory until you reach until the end. Unlike arrays are being actually reserving a complete block of memory, like a solid, okay, sorry for the solid bit, like a complete consecutive block without any interruptions. But in linked lists, you could actually allocate, an object to a certain part of the RAM, and then you can allocate another object somewhere else in the RAM, and literally you don't care. You just simply you have a pointer to some other part of the memory, and you are just simply hopping through the RAM around until you get to the object which you need. So actually, let's talk about the arrays versus linked lists here, so we can actually solidify this concept a bit. So if we put an array versus, if I know how to write today, linked lists, let me just push it right there. So here you have a constant time access. Meaning that I say array of 1 or array of 2, give me the second or the third element of the array, and I will get immediately that, right? Because what happens is we have arithmetic operation to calculate the memory address. Do you remember the offset bit which I was talking about? So this is basically speaking saying, if I say, give me array, so if you have an array of 10 elements and I would like to get the third element, yeah, I will just make a memory. This is actually my memory offset, and I will immediately get it by calculating the memory offset with the actual CPU, with the CPU instruction, which is excellent, right? This is, you get access in a constant time. However, in linked list, you don't have a constant time access, because if you would like to get the last element of the array, you need to for loop until the end so you can actually get the element, because you cannot actually get there by calculating addresses. You cannot get there by offsets. You need to get to every element, see where it's pointing at, and keep just going forward until you get the last element. Okay, so that's one. So this one on this side, actually, so this is happening a constant time access. This one depends on the speed of access, depends on number of elements. Okay, so this one depends on the number of elements. The fewer elements you have, the faster the access would be, right? Because you don't have to loop that much. Okay, here you have a fixed size memory. Wow, it's also glitching on me. So fixed size memory. Okay, and here no fixed size memory, right? You know, no wasted memory even. Also possible wasted memory. Can somebody tell me why you could have a possibility of a wasted memory?
Well, if it expands by 10 and we use 13 elements, there's like seven like elements that can be filled. It's a
Yeah, carry on.
well, then you have like seven places where the memory is wasted.
Yep.
I mean,
Yep.
you can. I don't know if there is a way to like calculate and shorten it afterwards, but I mean, it's
I mean, you can actually do these micro optimization, as I like to call it. But yeah, what you are saying is actually correct. So, the wasted memory will happen if you actually allocate more than what you need, because you are allocating a complete block of memory. So you could actually allocate 10 elements, but use only 5 or 7, and you have 3 wasted memory which you cannot actually use. And if you would like to get this back, you need to just simply either shrink the array size or just simply just live with a short memory, and that's it. But like shrinking the array sizes and these stuff, truncating the empty spaces, is like, I think it could be used in a very, very extreme cases where memory is like really, really needed. But memory is cheap nowadays, so I don't think people actually do that. However, we do defragmentation, which is another story on its own. We can maybe discuss it when we get to file structures. In pair 3. Yeah, this is the bit about the fragmentation. There you go. So memory might not be available in one block. Okay, so if your RAM looks like something like, I'm actually going to erase it from here, but just to illustrate a bit. Let's say you would like to allocate 10 element array or 20 element array, and you have like a piece of RAM here, and then this is like an empty space. So this is E empty. Come on. And right here is, let's say, build in, like this is being used, operating system, programs, whatever. And then you have another piece here, which is empty, for example. And then you have another like used piece of the RAM. And you need to allocate 20 elements. However, here you have a space for 10, and here you have a space for 10, right? So what you're going to do in this case, what we do is something which is called memory defragmentation, where we say, okay, I need to combine these two in one block. I will actually shift this block, shift this block to the right, so it can, like be borderline with this guy. And actually, we will actually get this space appearing right here. So it's going to be here. And right now we have 20 consecutive blocks. But this required us to defragment the memory. Now, obviously, you don't do that by hand, unless you are a system engineer or somebody who's actually going to be programming operating systems. Right now, you need to really think about these stuff. If you are making DBMSs or something like that, you're going to also think about these things. But for the time being, you really don't need to think about these stuff. You might also think about this if you are going to work on very high performance applications where you see that things are going weirdly slow and you don't understand why. And when you profile, you're going to see how your memory layout looks like. But this is like very, very niche problem, I would say. But in any case, it's a problem that's being solved by operating systems and other system engineers that already have solved these type of stuff. So you don't need to think about them, but I usually tell you what's happening behind the scene here. So let me actually like erase all of that stuff. Take this out all. Okay, good. So yeah, there's also a probable higher cost of insertion. In here, because do you remember like when you have to shift the rest of the elements of the array if you insert somewhere in the middle? Let's say that you would like to get, you have 100 element array and then you insert in the second place. Right now you have to shift like what, 98 elements to the right? So this is actually could be expensive for that. For such operation, there's a probability for it. On the linked list side, there's no need to set the size of a collection, of the collection rather. The next thing is there is a probable lower cost of at actually insertion. Because as you already have seen with Adil, that if you have an element, let's say here's 1, pointing to 2, pointing to 3, and you want to insert, let's say 4, whoa, hang on, let me just, and you want to insert 4 here instead of 2, all what you need to do is take that pointer, create the 4 object, right? Pick that pointer, make it point to actual, like, of course, you're going to hold this in a temp somewhere. Point it to actually 4. Take the temp which you already have saved that pointer and just make the 4 point to here. And right now you remove this. And right now you just inserted an element. So it's actually kind of cheap to insert an element in a linked list. Now, obviously, it's going to be more expensive if you insert it at the end because you need to loop until the end and then make the last null pointer. That's because this guy is pointing to null, right? You can just simply say, okay, instead of you being null, you're going to actually point to, let's say, 5 and make the 5 point to null, and that's it, right? So, but you need to for loop until the end. Now, one of the things is because people hated the idea of, like, I have to start every time from the beginning of the list, right? So what people actually have made is something which is called doubly linked list. Have Adil covered this with you? People.
Is it with the counter or no?
Like you have a element 1 pointing to 2, and actually, hang on, let me just make this better. So pointing to null, pointing to 2.
No,
and,
we have not covered.
Yeah, and 2 is actually pointing to 1. Okay, so right now you know about it. You can actually take it as a homework and try to implement it. It's actually super easy. If you have implemented linked list, right now you can actually implement a doubly linked list. And please share it. I would like to know if you are actually able to pull this off. And there you go. This is how it actually works. So you have the previous and the next. So this is null, let's say. However, this is actually pointing to 3. Now, the cool thing about this is that you could actually, if you are here, if your pointer is here, you can walk backwards. So this is actually kind of cool. Right now, you can actually navigate linked list a little bit faster. Of course, you are paying the penalty. Well, not a penalty, but you are actually using additional memory for additional pointer. But this is actually not biggie in case you needed actually that speed of navigation. Obviously, this will, if the size matters, this will add up, right? This additional pointer will add up. But since again the memory is cheap, nobody is actually really thinking about this thing unless you are working with humongous data. So this is actually a different flavor of a linked list. So just to write it down in an official manner, I would say that it has so elements. Oh, if I write down today correctly, elements can point to next and previous. And previous, let me write it here, and previous elements, enabling reverse lookup. So you can actually just walk backwards and that's it. Okay. So that's, that's regarding the linked lists. Okay. Now, moving along, let's actually talk about really quick the stack as a data structure, as an abstract data type, rather. Okay. This is the stuff which I will cover with you this week. So let's talk about this. All of you, I think, have encountered the stack at a certain point. And if you haven't used it in programming still, or in programming 1, a stack as an abstract data type. If you haven't used it in programming 1, probably you have encountered the Stack Overflow error, right? So let's talk about, I will actually discuss this in a minute, but let's actually talk about the stack as an abstract data type. So stacks, by definition, stacks are dynamic data type or dynamic data structure where removed elements is the most recently inserted. I'll describe in a minute what does that mean. This is a constraint policy. Which is called last in, first out, which people like to refer to as LIFO. Okay, last in, first out. So it's actually when we would like to, if I would like to rewrite this in a different way, like, so this is actually like the, let's say this is the official definition of what a stack is. So it is a simply, so a stack, basically, simply is a list, if I would like to rephrase it or paraphrase it, with a policy to add or remove an element from one end only. Okay? And that one end, that end is called, that end, let me just take the dot from here. And it's called the top. Okay? So you say remove an element from the top of the stack or add an element to the top of the stack. So you are always working with the top of the stack. Now it depends on how you represent it, how it's being represented in books. Sometimes people like to say, okay, here's the stack. This is the top of the stack, or some people like to call this the top of the stack. The main thing is just you be consistent with the representation. But the most popular is people look at the stack from the top all the time, right? Now, moving along with this, what a stack is the same thing as when you are washing the dishes and you are just simply putting the plates which you wash. So let's say you took a plate, you washed it, you put it on the table, and you take the next plate and you wash it and you put it above it, right? So the first plate, and I'm an awesome artist, I have to say. So you know what, this is the programmer art. So here's the first plate. Here's the second plate. Here's the third plate. Here's the fourth plate, right? So I washed each one of them. I just simply stacking them above each other. And if I would like to take a plate from that stack, I actually take from the top, right? Unless I'm unless you are an anarchist and you would like to say, okay, I'm gonna just simply take from the bottom, which is fine, you're an anarchist, right? But in any way, usually people, like normal people, take from the top of the stack of the plate. So just simply like pick the plate and go. So this is how actually a stack operates. You always, you know, like you stack the things and then you just simply take from the top. Easy peasy, lemon squeezy. Now here are actually the official operations of a stack. Now, honestly, I'm really apologizing for, again, the handwriting. It's just simply like, I'm looking at my screen share right now. It's like taking a slope downwards. And this just because my hands are like cramped between the screen and the keyboard in a very awkward way. So hopefully this will be fixed next time. Stack as an ADT has the following operations. Oh, for heaven's sake. Operations. I don't know how to spell today. Oh, wow. Operations. Fine. Insertion. Insertion, this is the first one, and it is actually called, which is called push. Okay, so when you say I'm going to insert or add an element to the stack, we say push to the stack. So remove which is called pop. So we call pop from the stack. You will never say so. You'll never hear. I think I haven't heard somebody who says stack.add or add to the stack. They say push from the stack, and then they tell me like pop from the stack. We never say add and remove from the stack. This is like the lingo of it. Then if you, some implementations, let's say in .NET Framework, they have something which is called peek, which is basically returns an element without removing. Which is kind of neat feature, I have to say. Okay. Then you have check if empty. You need to know at any point in time if your stack is just empty, and that's it. So where I can actually use a stack, right? Where the heck would I utilize that thing? Now, applications, let me just scroll this up a little bit so I can have more room for my poor hand, which I'm gonna hopefully not break. Writing like this, applications. Scroll even more. So for example, function calls. If you don't know what does this mean, when you call a function, your compiler, or not compiler rather, but your runtime, your CPU basically pushes when you are in the middle of a function and you call another function, it just simply pushes that function into a stack, right? This is a good reason why, for example, in recursion, you get a stack overflow, because if you don't have a recursion without an end, without an exit condition, you're gonna just keep filling up the stack. So let me elaborate on this. So I'll actually write it here, but then I will erase it, or hang on, let me write it here. So let's say that you have a function void, wow, glitched, void f1, right? And then you're doing your own stuff and having fun, and then you call f2, right? Which is somewhere, defined here, let's say f2, void f2, right? And then you are actually in the middle of the thing, and then you are having fun, and then you're saying, okay, I need function 3 to be called here, which is somewhere defined down in your code at void f3, okay? Which does some stuff, right? Now, here's the interesting stuff. Actually, your code also continues here. There's a code more continues there, and so on and so forth. Now, there is a problem with this. If you actually make an unconditional jump, if you're going to talk in an assembly terms, you need to actually have to know that you haven't finished this function yet. So let's say that I would like to run function 2. So the computer has this PC counter or program counter. So it says, okay, here's the next instruction, here's the next instruction, it just executes it. And then suddenly it sees a function call. However, we need to return back to finish this function because this function isn't finished yet, right? So in order to do that, it will just simply, the CPU will say, okay, I'm gonna push this guy into the stack, okay? And then return to it back again. So we have a stack. I'm going to push there F1. This is what your CPU would do. And then it says, okay, let's actually call F2. And then it says, okay, let's go to F2. So it actually just starts executing what F2 does. And then all of a sudden it sees F3. And it says, I'm not done yet with F2, but I need to run F3 right now. So I'm going to push F2 into a stack, so I can return to it back later. So it says, okay, I'm gonna push F2, right? And then it goes to F3 and it does actually like the execution normally. I'm actually done with the execution. Once it actually reaches the end, it says, the CPU say, okay, who's actually in the function stack? Who's actually has to be executed? What I have to finish? There's some debt or some stuff I haven't finished yet. So it will look at the stack and it says, F2 is there. I will pop that from the stack. So it just simply removes it from the stack and restores back the memory, well, actually the instruction address where it should actually jump. So it says, okay, I was here. Now it's time for me to continue. So it will continue. Once it finishes F2, it says, okay, is my stack is empty? Oh, it isn't. Actually, I have F1 still in there. So this one guy has been executed and removed. And right now we have F1. So it says, okay, pop F1 from the stack because I need to get its position or the program counter where it is actually in the instruction set. And then it says, okay, F1, time to execute everybody else in here. And then once it's actually done, the program is finished. And this guy is already empty, right? After we popped it out. So this is, for example, how it is being used in function calls. If you have recursion, let's say you are actually having recursion. I'm going to call this void recursion. And you have code, and then all of a sudden you say recursion again without an exit condition, right? So there's no exit condition for recursion here. What it will happen here is the CPU will say, okay, I'm not done with this. Now I need to call this. So it will push into the stack record or recursion, sorry. And then it will say, okay, let me actually execute this again. And then once it reaches here, it says, okay, I am not done yet with the previous function. I need to call this again. So just simply say recursion again. And you will keep doing this up until you run out of stack space. And then it says stack overflow, right? You are not like, there's no exit condition and you are just keeping piling up function calls, which the CPU cannot pop out anymore, right? So this is one use of the stack, at least on the CPU level and instruction levels. So let me erase all of this. The other one more application or a couple more applications here before we're out of time is you can use it when you can use it. Let's say you can use it to implement undo and redo. So if you have operations in your user interface, you would like to undo a certain operation, you just simply, whatever operation you do, you just push it onto the stack. And then when somebody would like to undo, you just simply say, give me the previous operation, I will just simply execute it again. And then you just simply execute that again, so you undo it. But once you do the undo, you push it into another stack, which is called the redo stack, right? So you can keep two stacks and pushing to undo or redo. Now, of course, this actually involves something which is called the command pattern. You need to implement that in order to make your life easy. So command pattern, check that out. Probably you're gonna encounter this in RS2, I think. I don't know if they cover. I don't know if it's being covered or not. But usually you have something which is called design patterns, and there are many patterns around that you might actually have a look at. So feel free to look at those stuff. Okay. And also one more example, which I've already run in the class, but hopefully we have time to cover this, which is called balanced parentheses. Okay. Now the balanced parentheses meaning that if you are actually writing a math expression interpreter, or let's say somebody would like to write, if I give you a string of of, for example, 1 plus 2 divided by, and then you open a bracket like this, for example, and you say the 3 times 4 minus, I don't know, 5 plus 3, and then you close, and then you close it like so. And this is a multiplication. So imagine that you would like to know whether these braces or parentheses are actually balanced. I don't know why this actually exists. So right now we can actually make, there you go, multiplication. What does it mean balanced? It means that if this is open, this has to be closed, right? And if this is open, this has to be closed somewhere here, right? So this is open, this is closed. This is open, this is closed. If you have something like this and this, these are not balanced because I need to close this guy. However, I encountered another different kind of closure, right? So this is what balanced means. So let's actually get grab some examples here really quick. I have actually implemented in the class the code for it. Probably we'll show you how to implement this one in the next one, but let us actually talk about some implementation detail before we dig into the code probably next time. So imagine that, so here's the examples. So let's actually talk about examples of balanced parentheses. So for the expression, if I give you this is actually balanced, right? If I actually give you this is also balanced. If I make something like this is not balanced, right? Maybe something like this. This is also not balanced. Okay, so this is like very simple examples. Now, one could argue, and they say, aha, okay, I would like actually to, I can solve this by counting, right? I can count how many open and how many closed. And if they are equal, that means that they are actually balanced, right? And for these use cases, it might be actually correct, right? However, you can actually get with an interesting edge case here. So imagine that you have an edge case like this. This is not balanced, even though the counting is correct, but this is not balanced. For example, this will be balanced, obviously. So this is a yes. This, let's see. This is a no, right? So this is like, you cannot actually have this as a balanced one. So what we are really saying here is, what is exactly the rule here? Can somebody give me a guess? What is exactly the rule that governs this? Come on, peeps. Give me an answer.
Well, in every squared bracket you have to find normal brackets, and we have to set what are open and closed brackets. I mean, I don't know what do you mean by rule.
What is exactly the problem? Like, how can you know? How can you solve, like, if you know exactly what the problem is, if you can describe what the problem is, you immediately found the solution. So why the counting doesn't work? Because if you think about this, counting worked here, but it didn't work here, at least for the negative problems, right? And okay, so basically the rule is every last open bracket or parentheses or whatever has to be closed first. So if I open this, this has to be closed first, right? If I look here for this guy has been opened, right? I'm actually following the same types here. How this guy has been opened. Is this guy a closure of this guy? No, because they are not of the same type, first of all, and it's not simply not the closure, it's an opening one. You push this one and you ask, is this guy is actually a closure of this guy? And you say, yes, actually, it's a closure of this guy. So what you do, you just simply say remove from the stack. So let's actually like do a step-by-step here, really quick before we wrap up. So let's say you are having this problem and you're actually trying to solve it with a stack. So here's the stack. And then you actually loop in a character by a character, right? So you see this guy, this is an opening bracket. You push it into the stack. Okay. And then you say, okay, give me the next character. Is this character or is this braces? Is this guy? Let me actually use a different color. Is this guy a closing bracket of this guy? It isn't. So I'm going to push it into the stack. Now coming up next, is this guy a closing brace for this guy? It is. So what you do, you pop this guy from the stack. Okay, moving along. Is this guy a closing of this guy? It isn't. So you push into the stack. Is this guy a closing of this guy? Yes. So you pop this guy from the stack. You move to the next character. Is this guy a closing bracket of this guy? Yes. You pop this from the stack. Your stack is empty. You are done with the full string. This is balanced. Okay. I will actually cover with you the source code next class, and we'll talk about the queues, and then we will move on to with the other topics. Do you guys have any questions? My advice to you is like try to see if you can write this code for balancing parentheses, and I will write my code next class, and then we can compare. Also, I would advise you that you could actually try, where is the applications? Try to see if you can like, let's see, can you try actually like to give it a shot regarding the undo and redo bit? Try to see if you can actually pull that off just for fun. I know it's actually advanced, at least for the second year for now, but I think it's a good exercise or probably if you can pull this off, then it's actually great. You actually you have a good command of programming in general. And it's actually a relatively easy thing to implement, just needs a little bit of thinking. So yeah. If there are no questions for me, then I guess, let me actually stop recording here.